Hello, Math Humans. We're going to do our last section of G today. We're going to be talking about applications of quadratic functions. So we're going to manage a quadratic function in a real-world context. So basically, we're going to do one example today that has many different parts. So the problem says the path of a ball thrown by a softball player can be modeled by the function h of t is equal to a negative 0.0110 t squared plus 1.23 t plus 5.50, where h of t is the ball's position in feet and t is equal to time in seconds. So I'm actually going to rewrite our equation so it's all on one line, and I'm going to write a negative 0.0110 t squared plus 1.23 t plus 5.50. And again, we're going to do this graphically. For those of you physics lovers, this is the projectile motion formula that shows the position of the ball after time and gravity, and then an initial velocity. So for us, we're going to put this handy-dandy equation in our grapher. So we're going to enter a negative 0.0110 x squared plus 1.23x plus 5.50, and I'm going to do a zoom 0 for a zoom fit, okay? So notice that here comes my graph, and I'm going to zoom out a little bit because I want to see the whole parabola. So I did a zoom 3 enter, and I'm almost there. I'm going to do it one more time, zoom 3 enter, okay? All right, there's our graph. And so we're going to find some information on our graph as we label it. So the first thing that they ask us to do is graph it, okay? So I'm going to find this point right here, which is the y-intercept. So I'm going to do second calculate, and I'm going to do a value where x is 0 because that's going to give me the y-intercept, and it tells me that it is 5.5. And then I'm going to go ahead and find this point over here. So I'm going to do second calculate 2 for 0, and I'm going to scoot over, go to the left of that point, hit enter, and then I'm going to cross, and I'm going to hit enter, enter. So this is 116.124. And so let's talk about what those numbers represent. This is the initial position of the ball. So at time is equal to 0, h of, we'll put a 0 right there, is 5.5. So that means that the ball is starting at 5.5 feet above the ground. Notice that it's our y-intercept in the quadratic equation. This one over here is the ball starts here, it goes up, and it comes back down. The x-axis is the ground. That means that is where the ball hits the ground, okay? So this point was, 0. So if it hits the ground, that means it's 0 feet above the ground. And this in our equation is going to represent time. So it's going to take 116.124 seconds for the ball to hit the ground, okay? So that's just explaining what the function actually looks like. So the next part of the problem says how high above the ground is the ball when it's thrown. So that means that is the initial position. So I'm going to rate h of 0 is 5.5 feet. Okay, so we've already answered that question by labeling our graph. And then the next one says, after how many seconds does the ball reach its highest point? Well, if you think about that on our graph, the highest point is going to be the vertex. So on my calculator, oops, I'm going to go back to my graph. I'm going to do second calculate, and I'm going to find the maximum, which is option number 4. Okay, and notice the first question that's asked is where is the left? So I'm going to go back to the left of the vertex, and then I'm going to cruise across to the other side, enter, enter, and it tells me that that happens at this point right here. I'm going to resketch it right here. So on my parabola, this point is 55.909 and then 39.884. So the way our equation is written, so h of t is equal to, so the x value is always going to represent time, and the y value is the height of the ball at that particular point in time. So it says how many seconds does the ball reach its highest point? So the time to reach the highest point is going to equal 55.909, and in this problem the time unit is seconds. Okay, so now we're going to keep going with our questions. It says how high is the ball? So I'm going to bring in this past one. Remember, this is the vertex of the parabola, so the height of the ball is here. So then the height of the ball is equal to 39.884 feet. So you can either use the tick mark or you can write the word feet. The next question says, how many seconds does the ball hit the ground? So again, I'm going to bring back our original graph. So remember, we found that when it gets here, here's how long it takes it to hit the ground. So we've already found that information by labeling our graph. So the time to hit the ground is going to equal 116.124 seconds. Okay. The next one is interesting. So it says, how far does the ball travel before it hits the ground? So this is our rate that the ball is moving. That's how fast the ball is moving. Well, there's a lovely formula that says distance is equal to rate times time. So we want to know how far does it travel before it hits the ground. So the rate is 1.23 feet per second. And we know that it takes 116.124 seconds to hit the ground. We found that number here. The seconds cancel, and it's going to tell me that it's going to take 142.833 feet. So my distance is 142.833 feet. So the next part of the question says, find the relevant or the practical domain. So basically what we have is an upside down parabola. So the domain of that is all real numbers. But the practical or relevant domain is what is going to be that part of the problem that actually makes sense. So the practical domain, or you can call it the relevant domain, is going to be from 0 to 116.124 seconds, because I only want to know what happens when time is equal to 0 and then when the ball hits the ground. So the relevant domain or the practical domain would be from time is equal to 0 to time is equal to 116. The practical range, sorry, got ahead of myself. The practical range of the ball, technically, it could be a couple of different things. We could talk about it going from 0 to the highest point of the ball, which was 39.884 feet. We could also talk about it starting at the initial height of the ball, but then that means we missed this piece down here. And so we're going to say that the practical range, remember those are the y values, is going to be from 0 to the height, the maximum height of the ball. Alrighty, so that is it for today. We just needed to walk through one kind of long example. See you soon.